To work through an example of one of these substitution problems to show a little bit more how these are supposed to work. I'm going to look at an indefinite integral. So again, this integral won't have bounds. I'm just calculating an antiderivative. And my integrand is going to be this function. I'll take the sine of x, and I will square root that sine function. And I'm going to multiply this by cosine of x. Now, if this were a definite integral, I'd need to make sure that I'm only looking at values of x where the sine function is positive. I can't calculate this thing if it involves taking the square root of a negative number. But since I'm just looking for an antiderivative, I'll be okay. I'm just looking for the indefinite integral. Now, what marks this as a potential substitution problem? I'm looking for some function, but also its derivative. If I can find both of those things in my integrand, then that would suggest to me that I actually do have a substitution on my hands, something that can clean up this integral. So I notice that underneath the radical sign, I have the sine function. I remember that the derivative of the sine function is the cosine function. And since I have both of these things in my integral, I think I can clean this up a little bit and rearrange it into something a bit more simple. Now, it's traditional to use the letter u as my new variable. Some books will even go as far as calling this technique a u substitution. But the particular letter that I use doesn't carry a whole lot of weight here. I will set u equal to the function that I saw. For this problem, it's the sine of x. And I'm going to use this rule to change the way that my integral is written. Now, because I'm working in integral calculus, when I change my variable, there is a corresponding change in the differential. This is the reason why we care about the differential when we write integrals. It tells us what our variable is supposed to be, but it also carries extra information about how quickly that variable is changing. So to calculate my differential here, if a u is equal to a sine of x, I would like the exchange rate. When the variable u changes, how much does my variable x change, and vice versa? And all I'm going to do is I'm going to take the derivative of this sine function, which I know is the cosine of x. But since I'm working in differentials, this will get multiplied by my differential dx for the chain rule. So what this equation is telling me is an exchange rate. My x variable can change by some amount. I'll call that dx. And that induces a corresponding change in the variable u. We call that change du. But the amount of change between my two variables is not one for one. there's a conversion factor that I have to multiply. And for this problem, I've determined that the conversion, the exchange rate, is that 1 du is worth a cosine of an x times a dx. This is really handy for me because that's exactly what I see in my integral. So I'm going to rewrite this integral using the two equations that I've come up with. The first one for changing the variable itself, the second one for changing the differentials. This integral can be rewritten now as the square root of u, replacing that sine function, all du. du is my replacement for cosine of x dx. Well, now I can calculate this indefinite integral. It might help to rewrite my integrand as a power function instead of a radical. So I know that my indefinite integral will follow the power rule for integrals. Previously, I called this the power rule for antiderivatives, but integral is a shorter word, so I might as well use that. I increase the exponent by 1. I divide by the new exponent. And because this is an indefinite integral, because this is an antiderivative, there is some unknown constant here. This problem was not given to me with enough information to figure out what the constant is, so I have to leave this plus c as a placeholder. Well, I can at least clean up that denominator. If I'm dividing by 3/2, that's the same as multiplying by 2/3, right? I just multiply by the reciprocal. But I'm not quite done with this problem yet. My integral problem came to me in x variables. You can actually see I wrote the wrong variable down here. Excuse me for that. When I solved it, I changed to some new variable I called u. But in order to have a meaningful solution to this, I need to convert back to my x variables. The question is phrased in terms of x, so the answer should be phrased in terms of x as well. Now, all I have to do is I'm going to identify where are the u's in my antiderivative, and I'm going to replace them. I'm going to turn them back into sine of x. So the antiderivative that I've calculated, the indefinite integral of the square root of sine of x all times cosine of x dx, we have calculated that this is equal to 2/3 of the quantity sine of x all to the 3/2 power plus c, the constant of integration. That's how it works.